Greetings, ladies and gentlemen. My name is Manoj Abraham, Regional Manager of Intumescent Coatings for Hempel Paints in the Middle East. I'm a civil engineer by education and have been in this field of coatings and linings for about 26 years, 23 of which have been in the Arabian Gulf. I've been involved in fire protection, structural fire protection, ablative coatings and intumescent coatings for about 18 years. And my special area of interest is durability of acrylic intumescent coatings. This presentation is based on a recent project that we completed where there were challenges for the asset owner, the contractor, applicator, and the steel fabricator on selecting the right intumescent coating for the environment that the structural steel was located in. So we're going to look at the challenges and the research which went behind to provide the correct solution and the additional third-party tests that were done to show the asset owner that the selection of the product was correct and appropriate. The asset owners were very clear that the steel structure needed protection against cellulosic fire protection. Because although located in a refinery, the buildings were going to be used for maintenance and warehousing. Therefore, there was no hydrocarbon fire scenario here. The building as such was about 2 to 3 kilometers from the shoreline. So the asset owner and the contractor were looking for guidance on selecting the correct acrylic intumescent coating for the environment the steel was located in. And there was a challenge on getting the correct guidance or following certain standards that would guide them towards that. And they approached the coating manufacturers such as us to basically provide support in this area. The buildings that required 1 hour fire protection was located in a coastal environment, as we looked at about 2 to 3 kilometers from the shore. But the internal structural steel was fully covered. The asset owner had specified that the externally exposed steel shall be protected to CX environment as per ISO 12944. As explained in the previous slide, the project specification referred to CX environment as per ISO 12944, and what you see here is basically an extract of ISO 12944 part 2 table 1, which shows what these different environments are starting from C1 to CX. We also see typical examples of what could be an internal environment and an external environment for each of these corrosivity category. And in C4, we see very clearly that coastal shipyards and boat yards would be classified as an interior location for a C4 environment. So we had to share the detail that although ISO 12944 is a great standard when it comes to corrosion protection, it does not really talk about fire protection. So we needed to follow a different standard for looking at durability of intumescent coatings. As explained earlier, the asset owner insisted that all structural steel shall be protected to CX environment as per ISO 12944. And the challenge was to tell them that CX could be applicable for the externally exposed structural steel, but for the steel buildings fully enclosed, sheltered, and ventilated with structural steel internally located would not fall under CX environment. The end user had a major issue from their perspective. And what they basically said was that the doors of these buildings will be exposed for a long time during the plant operations. They will not be able to close it. So they were thinking that since the door is fully open, would the internal structural steel be exposed to the coastal environment, the humidity that comes in during the summers, typically in the Arabian Gulf, would affect the coating system that is selected. So since it is cellulosic fire protection that was needed, so an acrylic intumescent would be more than sufficient to protect it from a fire perspective. But the end user, the asset owner, wanted to know if the acrylic intumescent coating that we selected would be suitable to withstand the aggressive environment that the steel will be exposed when the doors are open during the plant operation. The major challenge was to categorize the corrosivity environment that the internal steel was exposed to. So, in the absence of any data for corrosion loss, metal loss over a year's time, uh, what we did was to look at ISO 9223 and basically calculate the metal loss, the anticipated metal loss over a year. So we calculated and took data of the environment. We did an extensive literature survey, got details of the air quality monitoring stations, which gave details of the sulfate ion presence in the location. We also followed the design philosophy and the principle in that project where they increased the annual temperature to be on the conservative side. They increased the annual temperature. The annual temperature was in the average annual temperature was in high 20s, closer to 28, 27, 28. But we added additional 5.5 degrees centigrade in our design calculations. So that was done. We also, looked at the relative humidity from the meteorological data that was available, and we applied it to the formula that was available in ISO 9223 and arrived at a rate of corrosion of 48.97, almost 49 microns per annum. The formula recommended by ISO 9223 in the absence of physical metal loss measurement in order to identify the corrosivity category is shown here in the slide. So what we basically did was collect all the data uh, from the site. In fact, what we used was probably typical of an externally exposed steel, but we wanted to be very, very conservative when we calculated the corrosivity category because we did not want to error in any way. So when we did the calculation, as shown in the previous slide, it was coming only to about 49 microns per annum. And that typically, if you follow ISO 9223, which is also referred to in ISO 12944, any environment that has less than 50 microns would be classified as a C3. But again, this was on the very high side of C3 limit, which is up to 50 micron per annum. We have gone with the calculation, or our engineering judgment was that the steel within the building would be exposed to a C4 internal corrosivity category as per ISO 12944 or even as per ISO 9223. Based on the ISO 9223 calculations, it was clearly established that the structural steel at the maximum was exposed only to a C4 environment, even that internal. Right? So Hempel recommended that a solvent-based intumescent coating, which is tested as per EAD 3504022 to X category, should be used. So the complete system, including the primer, the solvent-based intumescent, and the polyurethane top coat, was recommended. The asset owner appreciated the work done in terms of the environmental classification and the justification provided, but they also wanted additional testing to check if the coating system that has been selected, the primer, mid coat, and top coat, can withstand C5 high environment as per ISO 12944. And if you look at ISO 12944 part 6, there are typical tests recommended, and the asset owner and the contractor wanted us to test the paint system, the intumescent coating system, to a C5 hive environment purely from a corrosivity perspective. That was the request and posed by the asset owner and the main contractor. The next few slides will basically show the uh, testing that was done as per ISO 12944 part 6 for a C5 high environment, and you can see that the results were quite outstanding, right? It was exposed to 1440 hours of artificial aging as per ISO 9227, and the results were that the coating system was able to withstand the corrosive environment, the accelerated testing as well. The test results from the neutral salt spray testing are clearly tabulated here, and you can see that the coating system consisting of a zinc phosphate based epoxy primer applied about 100 microns DFT, followed by a solvent based intumescent coating. The thickness was around 500 to 600 microns, followed by polyurethane top coat at 100 microns, uh, was excellent in terms of corrosion protection, and you can see that very clearly in this slide. So the coating system was able to withstand the accelerated weathering process. The photos that you see here are basically the results of the testing that was done for C5 high durability as per ISO 12944 part 6. And on the left side, what you see is the measurement of creep from the scribe that was put in, and you hardly see any increase in the width of the scribe. That is, there's no creep. And on the right side, what we see is the pull-out test and the results that we got after the neutral salt spray exposure, 1440 hours exposure. So you've got very good results of the complete system from the testing, again from a corrosion protection perspective. The summary of the testing as per C5 high durability testing is given here, and you can see that the coating system has passed the requirements and they have performed very well from a corrosion perspective. Now this was a prerequisite for the asset owners because they were concerned about the performance of the acrylic intumescent from a corrosion perspective. They were very clear because the product was already tested, the whole coating system was already tested to X category. So they were very sure that it will withstand cellulosic fire performance or protect it from a cellulosic fire scenario. But what they were concerned was the corrosion resistance perspective, and this test result provided that detail to them where they were now able to accept that the coating system provided meets or exceeds the accelerated weathering test required as per C5 high durability. Based on the theoretical calculations and the practical tests that were done on this coating system, which includes the zinc phosphate primer, the solvent-based intumescent and the PU top coat, we can see that the coating system recommended for the internal steel that was located in a C4 environment, uh, the solvent-based intumescent provided adequate protection and will provide adequate protection from fire and corrosion. As we know, during plant operation, the expectation of the asset owner is that the door will be open. Therefore, a coating system which is approved for X category as per EAD 350402 shall be used, and a water-based intumescent, a water-based acrylic intumescent shall not be used. Now, one of the challenges that we have addressed here was that there is no clear guidance to state that if it is a C4 environment, a water-based intumescent shall not be used. There was no direct guidance either from industry bodies or from standards to state that a water-based intumescent shall not be used in a C4 environment. So this attempt and this work that we have done is basically to show that we can identify the environment in places where the project detail is not very clear, but it also clearly defines that a product and a system, including the primer, mid coat and the top coat, tested to X category shall be used in a C4 environment. Thank you very much.